We are back in action after an entire week of being off because of coronavirus. I hope that you're all home and ready to get back to work. So, alright, let's pick up right where we left off. We were talking about kinematics, which is concerned with how objects' position moves in time, or position changes in time. We talked about a whole bunch of different things, a couple of which are average velocity, which I have written here, and average acceleration. So average velocity is the change in position over the change in time for some finite width of time, delta t. And average acceleration is change in velocity over change in time. So this is for some finite interval in time, but if you want to go to an infinitesimally small interval in time, then you're going to have to use calculus. So velocity then is the first derivative of position, and acceleration is the first derivative of velocity, or in other words, it's the second derivative of position with respect to time. Okay. So I wanted to derive for you a few equations in the very special case that acceleration is constant. So in the case that acceleration is constant, then we can talk about the kinematic equations at constant acceleration, or the KECA. These are very helpful equations. They'll be helpful for you in solving your homework problems. But one thing to keep in mind is that these are only applicable when acceleration is constant. So if acceleration is not constant, you cannot use these equations. Okay, let's talk about an object then that starts out at some initial time, ti, and goes up to some final time, tf. Its position starts out at xi and goes to xf, and its velocity starts out at vi and finishes up at the final velocity of vf. So, if acceleration is constant, then that means that the acceleration, the instantaneous acceleration, is equal to the average acceleration at every point in time, right? Because it's constant, it doesn't change with time. And the average acceleration is change in velocity over change in time, just by definition. So using the notation that we're going to adopt over here, that means this is velocity final minus velocity initial over t final minus t initial. Okay, so I can do some algebra here and multiply this both sides of this equation by this time interval. And I would have that a times t final minus t initial is equal to v final minus v initial. Or in other words, v final is equal to v initial plus acceleration times this change in time, t final minus t initial. Okay, this is a very helpful equation. I'll give it a number in a box. So this is the first of the kinematic equations at constant acceleration. Okay, next, just notice something. So we talked about how acceleration is the slope of the velocity versus time curve. Now, if acceleration is constant, then that means that the slope of the velocity versus time curve is going to be exactly the same for all values of t. So for every point in time, the slope of this curve will be the same. So that just means that the slope is constant, so this is just a line. So the velocity versus time curve is just a line. If I were to pick out some t initial, say, and some v initial, t final here, or v final up here, you note that the average velocity in this time window here between t initial and t final, our average velocity is just 1/2 of the sum of these two endpoints here. So the average velocity over this time window going from t initial to t final is just this value that's halfway between v initial and v final. So this turns out to be very helpful for us because we can take the definition of average velocity, change in position over change in time, or in our notation, x final minus x initial over t final minus t initial. And I can set this equal to this value here. So if I set this equal to v initial plus v final over 2, and let's say that I want to find, I'm more interested in the position and how the position changes with time rather than the velocity of this particular object, then I could take this equation here, I can plug in the final velocity that we derived in equation 1, and I would come out with x final minus x initial over t final minus t initial equals 1/2 times v initial plus v final that I'm going to plug in from equation 1. So plugging that in, here I have v initial plus acceleration times t final minus t initial. Okay. So I can just do a little bit of algebra on this. Note that these two v initials are the same, so I can have collect like terms here, 2 v initial plus a times t final minus t initial. And that would be equal to the same quantity there. If I distribute this 1/2, I'll have v initial plus 1/2 times acceleration times this time interval here. Okay. Now I'll take and multiply the left and right hand side by t final minus t initial. I'll get that x final minus x initial is equal to v initial times t final minus t initial plus 1/2 acceleration times t final minus t initial squared. And finally, I'll add x initial across, and you'll see that the final position is equal to the initial position plus v initial times change in time plus 1/2 acceleration times t final minus t initial squared. Okay, let's put a box around that. This is a very helpful equation when under constant acceleration, when you are interested in the velocity or the final position of an object after some time has passed, and you know the initial velocity, but say you don't know the final velocity, but you do know the acceleration. So lastly, let's say that you don't know anything about the time over which something takes place, and you're just interested in getting the final speed from the acceleration and the change in position. So in that case, you could write that x final minus x initial, say, equals v initial times, well, there's this time interval here, and there's another time interval here, but let's get rid of that. You can get rid of that by noting that, right, acceleration was v final minus v initial over t final minus t initial. All right, well, if I know the initial time and or if I know the speeds and I know the acceleration, then I can just get rid of this t final minus t initial, right? Initial divided by a, right? Just doing algebra here. And I can take that and I can plug it in here. I can plug it in there to get rid of time on both sides of this equation. So I'll have x final minus x initial is equal to v initial times v final minus v initial by a plus 1/2 times a times v final minus v initial divided by a squared. Okay, so a few things to note, right? I have an acceleration in the denominator here, and I have an acceleration in the numerator here, and 2 powers of acceleration in the denominator. So if I multiply by 2a on both sides, I can get rid of everything from the denominator. So let's do that. 2a times x final minus x initial is equal to 2vi vf minus vi plus, okay, so I had already said there's a 2 and there's an a in the denominator here, so those go away, and I'll just have v final minus v initial squared in the numerator. Okay, now let's factor out a few of these things on the right. So I'll have 2vi vf minus 2vi squared plus, now I'll factor out this term, v final squared plus v initial squared minus 2 v final v initial. Okay, so this term here cancels with that term there. And you'll note that, so there's a v final squared here, and there's a minus 2v initial squared and a plus 1v initial squared, so it just gives me v final squared minus v initial squared. So that means I'm just interested in getting v final squared, starting from a known initial, v initial, I can take v final squared equals v initial squared plus 2 times acceleration times this change in position. So this is the third of the kinematic equations at constant acceleration. So this is great. This is a really helpful, another really helpful equation. Okay, remember, all of these equations are useful only when you know that the acceleration is constant in time. Now, something else to keep in mind is that this this notation can get quite cumbersome at times, using v initial, v final, t initial, and t final. So sometimes we shorten this up a bit by using the initial time to be 0. We set the clock basically, right, t initial to be our 0 point. And we use, instead, t final, we just use up to some time t. We set x initial then to be x0, right, x at time 0. And the final time to just be x. And we set v0 to be the velocity at time 0, and v to be the velocity at the final time. And so sometimes it's very useful to have this longer notation, say, especially if you have 2 different time systems. So if you have a problem, say, where there's 2 objects that start moving at different times, and you need to find, say, when the 2 objects hit one another or something like that, then it's useful to have the time initial and time final explicitly written out. But compact notation is helpful sometimes as well. So under this more shorthand notation, the 3 kinematic equations at constant acceleration are v equals v0 plus acceleration times time, v squared equals vo squared plus 2ax, and the middle one that we had was x equals x0 plus v0t plus 1/2 a t squared. Okay, you'll see me use both of these forms to solve different problems. I prefer this, I prefer these shorthand notation when I don't explicitly need, say, different time coordinates, things like that. Okay, here's an active learning exercise. It's available to you. I'll put it in the link down below. I'll put a link in the description down below this video here. All right, an inattentive driver is traveling at 18 meters per second when he notices a red light ahead. His car is capable of decelerating at a rate of 3.65 meters per second squared. If it takes him 0.2 seconds to get the brakes on, and he is 20 meters from the intersection when he sees the light, will he be able to stop in time? Okay, so you can see here, I've gone through, I always, when I read these problems, I circle some of the information that I know is going to be relevant. It's good to start every problem by reading it twice. Second time through, make sure to circle things. And there's no picture given to you here, so I think it's very helpful to draw a picture. So there's two kind of phases here. It says that it takes him 0.2 seconds to get the brakes on in the first place, and that he's 20 meters from the intersection when he first sees the light. So there's this, I drew this up as if there's two phases here. There's phase one when his acceleration is 0 because this is the time that it takes him to get the brakes on. So it takes him 0.2 seconds to do that, and he's traveling at a velocity of 18 meters per second. So remember, the second kinematic equation at constant acceleration was KECA2 was x final equals x initial plus v0t plus, and then there was this 1/2 at squared term. But the acceleration here is 0, so that term is going to be 0. All right, so I can shorten this up by writing delta x for, say, x final minus x initial. And I'll say, right, I have delta x equals v0 times t then. Well, the velocity is 18 meters per second throughout the whole time, and it takes 0.2 seconds for him to get his foot on the brake. So delta x in this first phase here is going to be 18 meters per second times 0.2 seconds, or in other words, 3.6 meters. So he started out 20 meters away. He traveled 3.6 meters before he ever even got the brakes on. Okay, now what happens in phase 2? Well, in phase 2, his acceleration is so the problem says that he can decelerate at a rate of 3.65 meters per second squared. So that means he has a negative acceleration. He's traveling more slowly over time. And his initial velocity is now 18 meters per second. And it's going to take him a certain amount of, he's going to travel a certain distance and until he comes to a stop. Okay, so if he's coming to a stop, that means that his final velocity, v final, is going to be 0 meters per second. Okay, so stop is a key word here. Stop is going to imply, right, that the velocity is 0, right? So in this case, it's the final velocity because he's stopping at the end after all the dust has settled. And so let's find then the delta x for phase 2, and then hopefully when we sum those two delta x's together, they'll be less than 20 meters for this guy's sake. Okay, now here, note in phase 2, we have an acceleration, and we have a known initial velocity, and we have a known final velocity, but we don't know anything about the time over which this takes place. So we want to get the change in position. We want to get the change in position for phase 2. And we want to get it from the known starting and final velocities and the acceleration. Well, the kinematic equation at constant acceleration number 3 is the helpful one here. That said that v final squared equals v initial squared plus 2a change in x. Okay, so let's plug in all of our known values, right? So v final was 0, v initial is 18 meters per second squared, and acceleration is minus 3.65 meters per second squared. Okay, so 0 equals 18 meters per second squared plus 2 times minus 3.65 meters per second times change x. So let's just solve this for delta x. let's see, I would have 2 times this 3.65 meters per second times delta x equals 18 meters per second squared, and that would give me delta x equals 18 meters per second squared over 2 times 3.65 meters per second. If I put that into my calculator, this gives me about 44.38 meters. Okay, so let's say this is delta x for phase 2. Call this delta x2. Delta x1, the time that it took for him to get the brakes on in the first place, is this 3.6 meters. So the total distance that he's traveled then would be the 3.6 meters it took to get the brakes on plus 44.38 meters to come to a stop once the brakes actually got on in the first place. So he traveled about 48 meters total. And remember that the stoplight was only 20 meters ahead of where he was, so will he be able to stop in time? No, not even close, in fact. Another thing that you'll remember from what we talked about in the first week is that the free fall acceleration due to gravity is also constant. So the acceleration due to gravity is also known as little g, or 9.8 meters per second squared. Okay, so the free fall acceleration is constant. It's constant for all objects. It's constant in time as something is falling. It's independent of the mass of the object, or the chemical composition of the object, or anything that any of the particular details of the object. The only thing that's really important to keep in mind is that this is in the case where there is no air resistance. So that would mean, so if you have a coordinate system, say where y is pointing up, that's positive y, then the acceleration would be minus 9.8 meters per second squared, right, or minus g. If you choose your coordinate system where y is pointing down, that's where positive y is, then the acceleration is just positive g, or 9.8 meters per second squared. So any constant of nature that I give you will always be a positive quantity. Whether or not the acceleration is positive g or minus g just depends on which way you've set up your coordinate system. Let's apply this to a particular problem. So let's say there's a helicopter that is ascending vertically with a speed of 5.1 meters per second. And when it is at a height of 105 meters above the ground, a package is dropped from a window. Then how much time does it take for the package to reach the ground? Okay, so I drew a little picture here, right? We have a helicopter. The helicopter is going up. I put VH to show the velocity. The helicopter is going up, right? The package is dropped from the window, so VP shows the velocity of the package. Right? The package is going down, and it travels a total distance of 105 meters, right? And you have to choose a coordinate system, right? The y-axis could be pointing up or down. I chose it to be pointing down. So that would mean that the acceleration in the y direction is plus 9.8 meters per second squared. Okay, so there's this equation here that could help me. Change in y equals v0t plus 1/2 at squared. All right. How did I know to use this one? Well, I know that v0 for this package equals the speed of the helicopter, right? That's given to me in a hint here in this problem, but it probably didn't need to be given to me in a hint. I know, right, when this package gets dropped from the window, that its initial speed is going to be whatever the speed the helicopter is moving at. That makes sense, right? So this is going to be v0, and of course the velocity of the helicopter is going up, right? So that's in the negative y direction, since I've chosen the y-axis to be pointing downwards. So v0 is going to be here minus 5.1 meters per second, All right, and I know that the acceleration then is going to be plus g because I chose the y-axis to be pointing down. Right, so this is plus 9.8 meters per second squared. Okay, and I was asked to, and I was also given delta y, right? The total distance that this thing travels is going to be 105 meters. That's how long it takes to get to the ground. So I can plug all of these numbers in, and then I can solve for t. So I have 105 meters is equal to minus 5.1 meters per second times t plus 1/2 times 9.8 meters per second squared times t squared. All right, now I have one equation with one unknown, but it is not a linear equation, so I'm going to have to use the quadratic formula. All right, let's get this in a more familiar form then. So I prefer to get things in y equals ax squared plus bx plus c terms. So let's get that in, let's get this equation in the proper form. I would have 0 is equal to 4.9 meters per second squared t squared plus there'd be a negative 5.1 meters per second times t minus 105 meters. All right, so I'm going to solve this thing for time. So t equals, well, here in this format here, right, x is opposite b plus or minus square root of b squared minus 4ac all over 2a. So applying that here, I'm going to have 5.1 meters per second plus or minus square root of b squared, so 5.1 squared meters per second, 5.1 meters per second squared minus 4ac, right? A is 4.9 meters per second squared, and c is minus 1.105 meters all over 2a. It's 2 times 4.9 meters per second squared. Okay, so if I plug this into my calculator, I get that the time is going to be either minus 4.14 seconds or plus 5.18 seconds. Okay, now which one of these are physical? So this shouldn't be too difficult to figure out, right? The negative time is not a physical answer, right? The time that it takes is going to be 5.18 seconds. So here's one that we had started in class and then just, well, then coronavirus. So let's talk about this. The position of an object is given by this polynomial in time. X equals at plus bt squared, where x is in meters and t is in seconds. What are the units of a and b? The coefficients is the first question. So part A, what is the units of a and b? Well, I can write, right, x equals a times t plus b times t squared. And I know that I can, if I take the units of both sides of this equation, they'll be equal to one another. Okay, so I use square brackets to refer to the units of these quantities. So x, the units of x are in meters, and that's going to be equal to, right, the units of at, right, and that'll also be equal to the units of b times t squared, right? If you add two quantities together, and they're physically meaningful quantities, they have to have the same units. Okay, So that means that meters is also equal to, right, the units of A times the units of B, because when you multiply two quantities together, the units are just those two units of those two quantities put together. So that also means that that would be equal to the units of A, the units of T, and similarly equal to the units of B times the units of T squared. So time is in seconds, we were given that. So we then know that meters equal to the units of A times seconds equal to the units of B times seconds squared. So that implies that A is in units of meters per second, and B has units of meters per second squared. Okay, so A has velocity units, and B has acceleration units. So part B asks, what is the acceleration as a function of time? Well, we have a given position versus time, and if you remember, right, velocity is the first derivative of position. Acceleration is the second derivative of position. So let's take the derivative of our polynomial here. First, let's just get the velocity. So let's take the time derivative of the position versus time curve, which was AT plus BT squared. Okay, so you remember from the polynomial formalism from before that if you have some polynomial a x to the t to the, let's use t. So if you have some polynomial a t to the n plus b t to the m, you can take the derivative of that polynomial, and dp of t dt will be equal to a times n t to the n minus 1 plus b times m t to the m minus 1. So you drop the exponent by 1 and multiply the exponent out in front by the times the coefficient to get the derivative of a polynomial. So that would mean this has a times, right, t will be 1 t to the 1 minus 1 plus b times 2 is t to the 2 minus 1. So that means, well, a times 1 is just a, the 1 minus 1. We have a 2b, then t to the 2 minus 1. Well, t to the 1 minus 1 is just t to the 0, otherwise known as a 1. So this term is just a. And in the second term here, t to the 2 minus 1 is just t to the first power. So this is a plus 2b times t. So we were asked to find the acceleration, though. Acceleration is going to be the time derivative of the velocity curve. So d dt of a plus 2b times t. All right, so a is a constant. So when we take the derivative of a, it's going to be 0, right? The derivative of a constant is 0. Derivatives are rates of change. So if something is constant, by definition, it does not change. So its derivative, the rate of change of this constant quantity, would be 0. Now, the derivative of the second term, right, d dt of 2b times t, is going to be, well, you can just pull out by the constant multiple rule this 2b out in front. 2b times derivative of that 1 power of t that we had on the inside, right? And remember that the derivative of t to the first power was just 1. So acceleration is just 2b. Okay. So moving on to part C. It just asks us to plug in a specific value of time. So C says, what are the velocity and acceleration at t equals 5 seconds? So I can just plug in, right, v at t equals 5 seconds. It will be a plus 2b times 5 seconds. So in other words, a plus 10 seconds times b. I always box in my answers, and I think you should do the same on your exams and on your any written homework you get. And a is not a function of time, right? It's a constant value. It's 2b. So a at t equals 5 seconds is also just 2b. Cool. Now, part D asks, what is the velocity as a function of time if x equals, now we have a t to the n plus b t to the m. Okay, so x equals a t to the n plus b t to the m. Now what is the velocity? Well, v is dx dt. So we have a times n t to the n minus 1 plus b times m. Run out of space here. Plus b times m t to the m minus 1. Okay, so these would then have, because there's the power is changing here, that means that the coefficients would now have different units, but this would be the velocity polynomial in time for x equals a t to the n plus b t to the m. Now, what about if, in part E, if x is instead a t to the n times b t to the m? Or in other words, a times b t to the n plus m. Well, v is dx dt. So we have to take the, so there's the constant terms here that always stays the same by the constant multiple rule. Then I can take the exponents and multiply them out front. N plus m, t to the n plus m minus 1. And drop the exponent by 1. So that is our answer.